Good day, grade 10 learners! I am Teacher Anna and welcome to another Math Tonight episode. Today, we will learn about polynomial equations. Are you ready? But before we start, kindly prepare your self-learning module, your pen, and paper to write your solutions and answers as we progress with our discussion. Also, look for a place in your home where you feel comfortable and safe. And most importantly, prepare yourself to watch and listen carefully. At the end of this lesson, you are expected to illustrate polynomial equations and determines the roots of polynomial equations. Let's begin. If you are using the Mathematics Learners module for grade 10, kindly open it on page 82. If you are using the Compendium of Notes, turn it on page 36. Let's talk about polynomial equations. We've already learned about polynomials. But what is the difference of a polynomials and a polynomial equations? Basically, a polynomial equations is a polynomial, but it has been set equal to 0. These have the general form of a polynomials equated to 0, wherein again, x is a variable, a sub n minus 1, and so on and so forth are given constants, and n must be a positive integer and a sub n is not equal to 0. It's easiest to understand what makes something a polynomial equation by looking at examples. Example number 1. 2 minus x plus 3x raised to 2 minus 4x raised to 4 equals 0. This one is an example of a polynomial equation. Aside to the fact that it is equated to 0, it doesn't violate the definition of a polynomial. Example number 2. 3x raised to 2 minus 4x plus 1 minus x raised to negative 1 equals 0. This example is not a polynomial equation because it violates the definition of a polynomial. It has a negative exponent. Example number 3. Square root of 5 multiplied to x raised to 7 plus 2x raised to 3 minus x equals 0. This one is an example of a polynomial equation. Though it has a radical sign, it only belongs to the coefficient 5. Example number 4. Square root of 5x plus 3 equals 0. This one is not a polynomial equation because the radical sign includes the variable x, which violates the definition of a polynomial. Example number 5. The quantity 3x raised to 2 plus 2x r raised to 2 equals 0. This is an example of a polynomial equation because it doesn't violate the definition of polynomials. Now, you've learned what a polynomial equation is. But how do we determine the roots of a polynomial equation? Before we talk about that, one important note that you need to remember when identifying the roots of a given polynomials is the fundamental theorem of algebra, which states that if p of x is a polynomial equation of degree n and with real coefficients, then it has at most n real roots. For example, x raised to 20 minus 1 equals 0. The degree of the equation is 20. Therefore, at most, we have 20 real roots. Example letter B. X raised to 3 minus 2x raised to 2 minus 4x plus 8 equals 0. The degree of the given equation is 3. Therefore, at most, we have 3 real roots. Finding the roots of polynomial equations. In doing that, we have 3 methods. The first one is by applying the zero product property, which states that if the product of two numbers, let's say A multiplied to B, equals 0, then either A is equal to 0 or B is equal to 0 or both. For example, x plus 3 multiplied to x minus 2 multiplied to x plus 1 multiplied to x minus 1 equals 0. All we have to do is to equate them by 0. The first one is x plus 3. Equated to 0 will give us x plus 3 equals 0. Transposing positive 3 will give us x, which is equal to negative 3. The second one is x minus 2 equals 0. Transposing negative 2 will give us x, which is equal to positive 2. The third one is x plus 1 equated to 0 will give us x plus 1 equals 0. Transposing positive 1 will give us x, which is equal to negative 1. Then the last one is x minus 1 equated to 0 will give us x minus 1 equals 0. Transposing negative 1 will give us x, which is equal to positive 1. Therefore, the roots of the given polynomial equation are negative 3, positive 2, negative 1, and 1. Let's have another example. X plus 5 multiplied to x minus 5 multiplied to x plus 5 multiplied to x minus 1 equals 0. Again, we need to equate them to 0. The first one is x plus 5. Equated to 0 will give us x plus 5 equals 0. Transposing positive 5 will give us x, which is equal to negative 5. The second one is x minus 5 equals 0. Transposing negative 5 will give us x, which is equal to positive 5. The third one is x plus 5. Equating it to 0 will give us x plus 5 equals 0. Transposing positive 5 will give us x, which is equal to negative 5. Then the fourth one is x minus 1 equated to 0 will give us x minus 1 equals 0. Transposing negative 1 will give us x, which is equal to positive 1. Notice that negative 5 occurs twice. If that is the case, if a root occurs twice, such as negative 5, the root is called a root of multiplicity 2. If it occurs thrice, the root is called a root of multiplicity 3. Therefore, the roots of the given polynomial equation are negative 5, a root of multiplicity 2, 5, and 1. Now, grab your pen and paper and find the roots of the given polynomial equation by applying the zero product property. The given equation is x multiplied to the quantity x plus 4, which is raised to 2, multiplied to the quantity x minus 3, which is raised to 3, equals 0. Again, the given polynomial equation is x multiplied to the quantity x plus 4, which is raised to 2, multiplied to x minus 3 raised to 3 equals 0. Okay. Applying the zero product property will lead us to equate the given polynomial equation to 0. The first one is x. Equating it to 0 will give us x equals 0. Then the next one is x plus 4 raised to 2. Meaning to say, we have a root of multiplicity 2. X plus 4 equated to 0 will give us x plus 4 equals 0. Transposing positive 4 will give us x, which is equal to negative 4. Then the third one is x minus 3 raised to 3. Meaning to say, we have a root of multiplicity 3. X minus 3 equating it to 0 will give us x minus 3 equals 0. And transposing negative 3 will give us x, which is equal to positive 3. Therefore, the roots of the given polynomial equation are 0, negative 4, a root of multiplicity 2, and 3, a root of multiplicity 3. Let us now move to the second method in finding the roots of polynomial equations, and that is by applying the factor theorem. It states that the polynomial p of x has x minus r as a factor if and only if p of r is equal to 0. For example, find the roots of x raised to 3 plus 6x raised to 2 plus 11x plus 6 equals 0 by applying the factor theorem. In the given example, we don't see any divisor. Therefore, we need to think of a number that when it is divided to the given equation, we will come up with 0 as the remainder. Let us try positive 1. What if x is equal to 1 or x minus 1 is the divisor? What would be the remainder? In order for us to find out, we need to use the synthetic division. Doing that, we need to write the coefficient of the given equation. So we write 1, 6, 11, and 6. And the divisor is 1. We need to bring down the leading coefficient, which is 1. Then 1 multiplied to the divisor 1 is equal to 1. Then 6 plus 1 is equal to 7. Then 7 times 1 is equal to 7. Then 11 plus 7 is equal to 18. And 18 times 1 is equal to 18. Then 6 plus 18 is equal to 24. The remainder is equal to 24. Therefore, 1 is not a root of the equation and x minus 1 is not a factor. Let us try negative 1. What if x is equal to negative 1 or the divisor is equal to x plus 1? Following the steps in the synthetic division, again, we write the coefficient of the equation. We write 1, 6, 11, and 6. Bring down the leading coefficient, which is 1. Then 1 multiplied to negative 1 is equal to negative 1. Then 6 plus negative 1 is equal to positive 5. And positive 5 multiplied to negative 1 will give us negative 5. Then 11 plus negative 5 will give us positive 6. And positive 6 multiplied to negative 1 will give us negative 6. Then 6 plus negative 6 will give us 0 as the remainder. Since the remainder is equal to 0, therefore, negative 1 is a root of the equation and x plus 1 is a factor. The second trial implies that x raised to 3 plus 6x raised to 2 plus 11x plus 6 divided by x plus 1 is equal to x raised to 2 plus 5x plus 6. The expression x raised to 2 plus 5x plus 6 when equated to 0 is called a depressed equation of the given polynomial equation. The roots of depressed equations are also roots of the given polynomial equation. Thus, by factoring, the factors of the difference equation are x plus 2 and x plus 3. Again, the factors of the difference equation x raised to 2 plus 5x plus 6 are x plus 2 and x plus 3. Therefore, the roots of the polynomial equation x raised to 3 plus 6x raised to 2 plus 11x plus 6 are negative 1, negative 2, and negative 3. Negative 1 came from the second trial, while negative 2 and negative 3 came from the factors of the depressed equation. We are now done with the last method in finding the roots of polynomial equations, and that is by applying the rational root theorem. In this method, we will apply the fundamental theorem of algebra, which states that every polynomial equation of a degree n has at most n roots. Because if we already proved that the number of roots is equal to the degree of the given equation, then we don't have to check all the possible roots. For example, find the roots of x raised to 3 plus 6x raised to 2 plus 11x plus 6 equals 0 by applying the rational root theorem. Doing that, we need to get first the possible rational roots by following this form: positive and negative factors of p over factors of q, wherein p is the constant term while q is the leading coefficient. In the given example, the constant term is positive 6, while the leading coefficient or q is positive 1. The factors of 6 are 1, 6, 2, and 3, while the factors of 1 is 1. So we have positive and negative 1, 6, 2, and 3 over 1. In simpler forms, we have positive and negative 1, 6, 2, and 3. After identifying the possible rational root of the given equation, we need to check them if they will give us 0 as the remainder by using the synthetic division. Let's begin with positive 1. Applying the synthetic division, we will write the coefficient of the given polynomial equation. We write 1, 6, 11, and 6. Then bringing down the leading coefficient, which is 1. Then 1 multiplied to 1 is equal to 1. Then 6 plus 1 is equal to 7. Then 7 multiplied to 1 is equal to 7. Then 11 plus 7 is equal to 18. And 18 multiplied to 1 is equal to 18. Then 6 plus 18 is equal to 24. The remainder, when we divide 1 to the polynomial equation, is equal to 24. Therefore, positive 1 is not a root of the given polynomial equation. Let's now proceed to negative 1. Again, following the step in the synthetic division, we write the coefficient of the given equation. We have 1, 6, 11, and 6. Bringing down the leading coefficient, which is 1. Then 1 multiplied to the divisor negative 1 will give us negative 1. Then 6 plus negative 1 will give us positive 5. And positive 5 multiplied to negative 1 will give us negative 5. Then 11 plus negative 5 will give us 6. And 6 multiplied to negative 1 will give us negative 6. Then 6 plus negative 6 is equal to 0. In this case, the remainder is 0. Therefore, negative 1 is one of the roots of the given polynomial equation. Then next is positive 6. Applying the synthetic division, we also write the coefficient of the given equation. We have 1, 6, 11, and 6. Bringing down the leading coefficient, which is 1. Then 1 multiplied to the divisor 6 will give us 6. Then 6 plus 6 is equal to 12. Then 12 multiplied to 6 is equal to 72. Then 11 plus 72 is equal to 83. Then 83 multiplied to 6 will give us 498. Then 6 plus 498 will give us a remainder which is equal to 504. The remainder is equal to 504. Therefore, 6 is not a root of the given polynomial equation. Then next is negative 6. Again, following the steps in the synthetic division, we write the coefficient of the equation. We have 1, 6, 11, and 6. Then we need to bring down the leading coefficient, which is 1. Then 1 multiplied to negative 6 is equal to negative 6. Then 6 plus negative 6 is equal to 0. Then 0 multiplied to negative 6 will give us 0. Then 11 plus 0 is equal to 11. Then 11 multiplied to negative 6 will give us negative 66. Then 6 plus negative 66 will give us negative 60. The remainder is equal to negative 60. Therefore, negative 6 is not a root of the given polynomial equation. Just a recap. Before we proceed in identifying the other roots of the given polynomial equation, the degree of the given equation is equal to 3. Therefore, at most, we are expecting that we have 3 roots. As of now, we've already identified one of the roots, and that is negative 1. Now, let's proceed in checking positive 2. Again, following the steps in synthetic division, we write the coefficient of the given polynomial, and that is 1, 6, 11, and 6. Then we need to bring down the leading coefficient, which is 1. Then 1 multiplied to the divisor 2 will give us 2. Then 6 plus 2 is equal to 8. And 8 times 2 is equal to 16. Then 11 plus 16 will give us 27. Then 27 multiplied to 2 will give us 54. Then 6 plus 54 will give us a remainder which is equal to 60. The remainder is equal to 60. Therefore, positive 2 is not a root of the given polynomial equation. Let us try negative 2. Again, following the steps in the synthetic division, we write the coefficient. We have 1, 6, 11, and 6. Bringing down the leading coefficient, which is 1. Then 1 multiplied to negative 2 will give us negative 2. Then 6 plus negative 2 is equal to 4. Then 4 multiplied to negative 2 will give us negative 8. Then 11 plus negative 8 will give us 3. Then 3 multiplied to negative 2 will give us negative 6. Then 6 plus negative 6 will give us 0. The remainder is equal to 0. Therefore, negative 2 is one of the roots of the given polynomial equation. We have identified the first 2 real roots of the given equation, which is negative 1 and negative 2. We are now down with the last one. So let us continue checking the possible roots. Let's proceed to 3. Following the steps in the synthetic division, again, we write the coefficient of the given. We write 1, 6, 11, and 6. Then bringing down the leading coefficient, which is 1. Then 1 multiplied to the divisor 3 will give us 3. Then 6 plus 3 will give us 9. Then 9 times 3 will give us 27. Then 11 plus 27 will give us 38. Then 38 multiplied to 3 will give us 114. Then 6 plus 114 will give us 120. The remainder is equal to 120. Therefore, 3 is not a root of the given polynomial equation. Then the last one is negative 3. Again, following the steps in the synthetic division, we write 1, 6, 11, and 6. Then we need to bring down 1. Then 1 multiplied to negative 3 will give us negative 3. Then 6 plus negative 3 is equal to 3. Then 3 multiplied to negative 3 will give us negative 9. Then 11 plus negative 9 will give us 2. And 2 multiplied to negative 3 will give us negative 6. Then adding 6 and negative 6 will give us 0 as the remainder. Therefore, negative 3 is one of the roots of the given polynomial equation. In this example, we finish checking all the possible roots before we identify the 3 roots of the given equation. So again, the roots of the given polynomial equation are negative 1, negative 2, and negative 3. While the factored form of the given polynomial equation is x plus 1 multiplied to x plus 2 multiplied to x plus 3 equals 0. And that's it. The 3 methods in finding the roots of polynomial equations. Just a recap, we have by applying the zero product property, by applying the factor theorem, and by applying the rational root theorem. Again, this is Teacher Anna, and see you on another Mathenic episode.